Hello, my name is Matthew Shu, and I'm currently a third-year PhD student at the Veramag laboratory and at Calray. My thesis advisors are Claire Meizat, Pascal Raymond, and Benoît Dupont de Dinechamps. And today I will present you the challenges in multi-core implementation of critical data flow applications, which is a subject at the core of my thesis topic. So I'll start with a brief presentation of the two institutions to which I'm attached. The first one is the Veramag laboratory. Maybe you're probably more familiar with it. And it's specialized in methods and tools for the development of safe and secure cyber physical systems. It is now organized in teams, the lab, and I'm part of the shared resources team, which tries to investigate the development of embedded systems that are constrained to shared resources. And these resources can be time, energy, or even communication mechanisms such as the memory. And the second institution is Calray, which is a company that designs many core VLI double V processors. And it's currently in its third generation of the MPP8 that contains 80 cores, and it's organized in 5 clusters. And it also, well, the MPP8 also contains other interesting architecture mechanisms for high performance and also time predictability. So now let's introduce our application domain, critical systems. And they are basically everywhere in our modern lives. And some examples would be the control systems of planes, cars, and trains. These systems are typically also hard real-time systems, meaning that not only the result of the computation must be accurate, but it also must arrive before a given deadline. So here in the figure, we can see an example of such a system with sensors acting as inputs to a controller that is responsible for the computation and actually the implementation of the programs that we'll see later on the presentation. And then it outputs commands to actuators that interact with the environment, and the environment provides feedback to the sensors. And all the steps contained in this loop must be executed within a certain time limit that, if it's not respected, it can provoke serious damage either to human lives or the environment. So to develop such systems, engineers typically employ some high-level language that are a little bit more abstracted than the C language, than the pure C. And one example are synchronous data flow languages that they try to abstract away the temporal aspect and provide a zero execution time abstraction, allowing the engineer to focus on the functionality of the system. And the programs written in this language can be seen as directed acyclic graphs, or DAGs, where each node of the DAG is a computational unit, and the edges represent precedence constraints that we have between the nodes, and also the communications that happens between them. Here we can see one example of such a DAG. It's really simple, contains only 4 nodes, and reads inputs from the environment and outputs. And some examples of these languages are Lust, which is well known in the academy, SCADE, which is an industrial, kind of started with as an industrial version of Lust and then evolved to a different path, and Blech, which is a new synchronous data flow language developed by Bosch that tries to modernize a little bit this abstraction and provides even more facilities to to a system engineer. So now the first challenge that I want to raise in my presentation is actually how to take this data flow model and implement it on a multi or many core platform. And here I can highlight several difficult steps that appear in this process, such as the first one is actually to extract the parallelism that we can see here easily in this model, because it's a simple example, but these applications can be huge. And once the parallelism is extracted, how do we efficiently implement the communication between the nodes and the synchronization that is needed to respect the precedence constraints while still respecting also the deadline. The second challenge is actually to map and schedule these nodes onto a multi or many core platform. And in this regard, we can choose how many cores of the platform are we going to use, or how many clusters also for a many core. And within a given core, the order of the nodes that will be executing in that core. And finally, how to orchestrate all this together at runtime, either choosing, for example, a time trigger execution, which is something that we employ, but other approaches use, for example, event trigger execution or dynamic schedulers at runtime or other mechanisms. So once we start to run these nodes simultaneously on different cores, we are subject to generate interference. In the small example that I've shown, we can see that here the nodes N1 and N2 are mapped to core 0, and nodes N3 and N4 are mapped to core 1. And here on the right, we can see a possible schedule of this program. And we see that nodes N2 and N3, they interfere with each other, basically because they write to the same target node in this schedule at exactly the same time. So they slow each other down, they generate a delay on the system, and this makes the actual release date of the node N4 a little bit later. So in a multi and many core platform, the worst case execution time of a task is not sufficient anymore, and we have to take into account the interferences that appear at runtime. And the challenges that appear here are actually how to correctly evaluate the interference delay that will occur between all the nodes in a program, and how to compute the overall time impact that this will have on the system in the global response time. And typically this is done for a given architecture because it really depends on how the nodes communicate with each other. And another interesting problem that we can see here is the different execution models that we can generate during the implementation of a synchronous data flow program. We have seen before that the nodes, they communicate with each other, which implies that intrinsically they have a read and execute and a write phase. And here I'm showing basically the typical execution models that we see in the literature. We can take a single phase approach where the read, execute, and write phases are all condensed into a single node, which is here called N1. Then a two-phased approach where we decouple the write phase from the node and generate an additional job called write N1. and a three-phased approach where we decouple the read and the write phases, and which are basically the phases that interact with the memory, and the execute phase of the node. And one can be executed in complete isolation. For example, if we have an architecture that provides memory privatization features for the data and the code of the task N1. So the challenges that appear here are actually to understand for a given architecture and for the criticality that we want in an implementation, if it's worth to actually split the tasks and how many splits can be done. How many splits is the optimal solution for a given architecture and a given program. And this depends a lot on the memory hierarchy of the platform and the arbitration that is done between the cores. Okay, so we have seen that implementing critical data flow applications in a multi-core platform is definitely not a trivial problem. There is no off-the-shelf answer, and the solution actually depends a lot on the target architecture and the characteristics of the application. And the challenges that I have shown, they all provide a compromise between complexity and precision. And in particular, for example, in the interference analysis computation, where we can take a really precise approach to compute the interference that does not scale well for more than dozens of nodes and cores, or we can take a really naive approach and assume interference on all the time, which will generate a really high global response time in the system. So everything is a compromise, and the goal is to find a good balance that will scale well for multi or many core architectures. And we have seen that incorporating the hardware knowledge can really ease the approach. And here I can give my testimonial that working at Calray has really helped to understand the intrinsic details of the architecture, how the memory arbitration is done. And even with this privileged information and exchange with the hardware architects, it has not been easy. And for generic platforms where we don't have this information open source, it can be an even more challenging task. So I've shown some of the ongoing challenges that the research community has faced, and we also study. And I would also like to highlight that we are currently developing a framework to be integrated with the industrial tools developed by ANSYS, which continues the development of SCADE, so that the whole code generation part is integrated with the timing analysis for the MPPA tree. So the system engineer can only design the program in the SCADE suite platform and target it to the MPPA tree, and all the code generation and the global response time calculation will be done automatically, improving a lot the development time that it takes to actually deploy the solution on the MPPA tree. And some future challenges that we are investigating and the research community also tackles is the efficient mapping and scheduling of huge applications in many core platforms that can contain hundreds of cores. So to really understand if the existing algorithms are enough to scale well with hundreds of nodes, or if we have to develop new solutions that will give a good response time and also scale well. And really the cherry on the top will be to develop a generic methodology that could take a synchronous data flow program and deploy it well, computing the interference on a given architecture. But for that, we need more open source description of the architectures, at least some standard that links them. For example, the shim standard exists, and it could be a good entry point for such a generic framework. So here are the 2 published papers that I've worked on and are directly related with what I've presented today. So do not hesitate to read them if the topic interested you. I will probably share also the slides. So if you want to search them later on, they'll be available on the Slack. And thanks for your attention. And if you have any questions, I'm available.